so see that we still have the former yellow chalk. This has not been fixed yet. We're still working on that. So it's another physics project, and a number of people asked a great question: what is general relativity? So I guess everyone that went on their break week early is going to get to learn about this. So this is actually this is probably a 2-weeker, and also I wanted to get to an example on basically RC circuits, and so I'm going to break this up into 2 parts. We'll revisit it at the end of the week after the break. But I think it's interesting to know, so maybe I'll pull a class. So how many people have used general relativity in the last week or so? I don't see any. I got Dave at the back, a couple here. So how do you think you used it in the last week? GPS, right? So basically clocks run at different speeds, at different heights in a gravitational field. And so when they first deployed basically GPS satellites, the clocks on Earth were not in sync with the clocks in satellites, which are further away from the Earth. And so we actually need the equations of general relativity to sync up those clocks. So if you've used any GPS on your phone to find you somewhere, or to use a reminder app that tells you, reminds you to do your physics checkpoint when you get home or something like that, you're basically using general relativity. All right, so basically the idea is that this is really the unification of special relativity and the Newtonian theory of gravity, and so we'll come back to this. We're actually not specifically going to talk about general relativity beyond this slide today. I'm going to motivate why we need it, and then we'll come back to it next week. As I said, this is a multi-parter. And so basically it's this connection between the energy momentum density and the geometry or the curvature of space-time. And this is really through special relativity in E equals mc squared. So normally we think of gravity being related to mass, but if we now have this basically, the equivalence between energy and mass through E equals mc squared, then energy must also lead to a gravitational field. And that's basically this energy momentum tensor right here. So these are basically just constants. G is the same capital G that shows up in Newtonian gravity. C is the speed of light. And so what this is saying is that the energy and momentum density of space-time, of the stuff that's around, leads to some curvature of local space-time. And trajectories in this general relativity, when we have bodies moving through curved space-time, they don't follow straight lines necessarily, but they follow something like a geodesic, the shortest distance between 2 points in the presence of curvature. Again, we'll come back to this a little bit more. And there's all kinds of really cool and testable predictions of general relativity. We've already seen this one, gravitational lensing, right? Because of light traveling in these straight lines through curved space-time, we see these multiple images. We've already talked about how you can get redshift when things are moving. This one's hard to see. This is basically the bowling ball on a mattress picture where a heavy body bends space-time around it. And then part of the motivation, and one person admitted to it in the wiki, was that they had seen Interstellar and wanted to know about black holes. I actually haven't seen Interstellar yet. Hopefully I'll watch it at some point. But I know that Kip Thorne and others were integrally involved in trying to make as realistic as possible some of the stuff in that movie. Okay, so these things don't happen in a vacuum. It's not like Einstein was just sitting around and said, oh, I really want to unify special relativity in the Newtonian theory of gravity, right? Why do we come up with new theories? We come up with new theories because the best theory at the time, so we basically advance, let's say technologically, or there's a new experiment or new discovery that no longer syncs with the current theory that we have. Right? And so basically we had Newtonian gravity. It worked extremely well. We could predict all the orbits of the planets. This is hundreds of years old. But finally there were starting to be some measurements kicking around, or some experiments that were saying, okay, things are not, maybe we need something more. Maybe the theory that we have is not the complete theory. And to really, we need to go really far back to motivate this, all the way to Galileo. And the point is that we're very familiar with Newtonian mechanics being invariant under Galilean transformations. So what's a Galilean transformation? Basically just says I have some reference frame, and then I have some other inertial reference frame which is moving with respect to the initial one with some velocity v. Right? So this is the classic like throwing a ball in a train car moving at constant velocity. Right? So basically I can't tell that if I'm really traveling at constant velocity, then I can't tell that I'm moving at constant velocity by doing some local physics experiments. Unless someone tells me, right? Newtonian physics will act the same. So I throw up a ball with respect to me moving my train car, it's going to follow the same trajectory locally. And so these are really the postulates of Newtonian mechanics under Galilean relativity or Galilean transformation. Basically, there's some absolute space. Newton's laws are true, and an inertial reference frame is a reference frame in relative uniform motion to an absolute space. So we're not accelerating, basically. If we're accelerating, then we need some fictitious forces, make-up forces, to try to understand what's going on. And this is a very important thing, that all inertial frames share universal time. So note that t prime is equal to t, right? So if I'm in this frame or in this frame, and we both start our stopwatches at the same time, then they're going to collect time at the same rate, and they'll agree later on. So that's kind of the two important postulates. And so we can see why this works by just looking at f equals ma. So here's my f equals ma, second derivative of this position vector, let's call this r, is going to be x, y, and z. So now I say, okay, what about, how does f equals ma look in this translating frame, in this inertial translating frame? Well, if I do this, I see, okay, so the only coordinate that I'm moving in is the x direction. And so I want to say, what is the temporal derivative of x? Well, I can just use the chain rule here, and I see that I get this additional term, right? So this is not surprising. Excuse me, the velocity is basically the velocity in x, and I have this minus v coming from this, right? But if I take another derivative, because I assume this velocity is constant, that's the crucial point. The velocity is constant, which means that we are not accelerating, right? The velocity is not changing in time. So when I take that second derivative over here, it just cancels out. And so basically the acceleration is the same in both frames, as long as this is an inertial frame. So Newtonian mechanics, which is basically this equation right here, f equals ma, doesn't care which of these frames I'm in. Right? So that's basically Galilean relativity in terms of Newtonian mechanics. But this class is all about electricity and magnetism, and so the kind of goal of this class is to derive these four equations. These are Maxwell's equations. And so far, we've really only seen this one. So note that the other ones all have v in them. So we're going to derive these in the coming months or so, and this will be exciting and fun. So these are the Maxwell's equations in so-called integral form. We have Gauss's law, as I said, the only one we've seen before. I can write these, so this is the so-called integral form of Maxwell's equations. I can also write them in a differential form. So this right here is Gauss's law in differential form. This is a very cool one. Someone else asked a question about this, which is equivalent to this. This is the no magnetic monopoles, right? The magnetic field is divergence free. I can't have a source of magnetism that just sits somewhere in space. So these are a set of differential equations. They're partial differential equations. So last time we solved a simple ordinary differential equation. One could use similar methods, related methods anyways, to solve these. And what we'll find when we do that, and we'll do this in this class, is that one class of solutions, or a class of solutions, looks like a wave equation. This is the solution for the x component of the electric field. So what this looks like, if we analyze this equation, and people might have seen equations that look like this for one-dimensional waves in Physics 51. So this is a wave equation for a wave that's traveling with some speed c, or certain c. And this c can be constructed in terms of these universal constants that show up in Maxwell's equations, the permeability and permittivity of free space. And this is what gives us our 3 times 10 to the 8 meters per second. So this is already pretty exciting. You solve these Maxwell's equations just using mathematical methods, and you find a wave equation. So the solution is that the electric field is a wave, and that wave is traveling with a velocity that doesn't depend on anything but universal constants, right? So this is the speed of light in a vacuum, and the speed of light is constant, and that's an important point. So now we can say, okay, we have Newtonian mechanics being invariant under Galilean transformations. What happens if we try to figure out, so this is really, a statement of physics should be the same in all inertial frames, right? That's really the statement of Galilean relativity and Newtonian mechanics. So we can ask the same thing about Maxwell's equations. So is electricity and magnetism the same in all inertial frames? Does this equation, which is just a combination of all these equations, satisfy, does it look the same under a Galilean transformation or a Galilean boost? So what I can do is, so I have this equation, right? And I can just see what happens, similar to what I did for Newton's laws, if I plug in this Galilean boost, where I just say, now notice, because I solved this is propagating in the z direction, I just imagine that my frame is now translating in the z direction. And the answer is no. It does not satisfy Galilean invariance. So how do I figure that out? Well, I say that in the new frame Ex prime, that I just sub in the coordinates, right, that I have for my boosted frame. And then now I have to actually act with these partial derivative operators. And the key point here is that this partial derivative with respect to t, this thing's called the Del Maestro, I think. Del Maestro, yes, I believe that's right. If I do this partial derivative with respect to t, what am I going to have? Well, now t shows up here, right? So if I actually want to compute this thing, so I have my e x prime as x, y, z minus bt and t, right? So if I want to look at partial with respect to t, then basically I need to realize the fact that t shows up in two places explicitly, right? So this partial derivative with respect to t now looks like basically v partial with respect to z prime, and then I have a plus partial with respect to t. And so when I act with this, or when I basically just plug this in right here, I get these two extra terms, right? So the only thing to take from this that looks like a lot of, this is essentially just algebra mixed with doing some partial derivative, but the important thing to take from this is this was our original equation. Now I do this Galilean boost, I say, what's the solution of Maxwell's equation in this inertial frame, right? I haven't talked about acceleration, everything's still moving at the same speed, and I get these extra two terms. So this is telling me that Maxwell's equations look different in this inertial frame, right? I have this extra term. But anyone notice anything special about this particular term? So why did it take so long before we needed special relativity? We had Maxwell's equations long before special relativity. Why didn't we need it before? What shows up right here? Anyone have any ideas?
Non-linear differential equation.
So that's certainly true. This thing's a bit of a mess to solve. What about, so this v is the speed that our frame is moving with, our inertial frame is moving with, right? And the speed of light shows up in the denominator squared. Yeah?
Isn't the partial the one of those terms, like one is, it looks like one of those is the partial, is like the partial, and one is like the original.
Yeah, so that's certainly how we get them, right? We get them by computing this chain rule and coming down the tree diagram. But I just more mean in terms of what would be, so let's say we could, why could we ignore these terms? When would these terms be small? That's what I'm trying to get at.
V is large.
They're small when v is small with respect to c, right? So we didn't need this. This is, this reason why we didn't need this stuff for a while. Maxwell's equations seem to work fine because unless v is basically on the order of c, c is 3 times 10 to the 8, right? And so what are the types of speeds we move around in on Earth in the 19th century? Maybe I'm driving around in my Model A or something like that at a couple of meters per second, right? This is really, really small. So I think this is a beautiful example of when we need to uncover new physics. We uncover new physics when we access new technologies that allow us to explore previously unexplored regions of phase space. Right? We were never traveling fast enough before or had measurements where these terms really mattered. Because up to the accuracy of our measurement devices, if v is a couple meters per second and c is 3 times 10 to the 8, then these terms are basically not important for any solutions of Maxwell's equations. Yeah?
Well, like, even if you're flying in a jet, that's still a very small fraction of the speed of light.
That's exactly right. So it's some combination of our ability to measure things increases and our ability to access new technology increases. So we can start getting more decimal places in our measurement devices, essentially. And so these just weren't noticed. These corrections were not important until we started coming up with a few places where they were important. And then all of a sudden, we think, oh geez, Maxwell's equations don't satisfy Galilean relativity. Maybe we're completely wrong. Well, the answer is not that we're wrong, we just haven't uncovered that new physics yet. Is that a question?
Are they important for setting things out of space, at really fast speeds?
Yeah, so they'd certainly, if we're traveling, let's say, in a spaceship and we want to try to pass a signal somewhere else, exactly, these things are important. Or, as I said, if we want to measure things to very high accuracy, right? And there already was a few kind of little problems that people tried to sweep under the rug about this type of stuff that were starting to knot people, and so it's really not, the precession of the perihelion of Mercury. That's what we're going to need general relativity to understand. And so these things kind of lay under the surface. There's some things that irk people or maybe just not. We don't fully understand them, and that is exciting because if we don't understand something, it means that there's some new physics out there that we might be ready to understand. All right, so this is basically, this problem right here is what led Einstein to posit special relativity. And so the idea there, special relativity basically has two postulates. The first is similar to the other one of Newtonian relativity. So basically the laws by which states of physical systems undergo change are not affected. Whether these changes of state we refer to the one or the other of two systems in uniform translatory motion relative to each other. So this is just basically a complicated way of saying that physics shouldn't really change too much in these inertial frames traveling with respect to each other. But this is the new one right here, really. This is the important piece, the principle of the invariant light speed. So basically the way that we can solve this problem is by saying that light always has a constant speed, 3 times 10 to the 8 meters per second. There's no ether, there's no substance that it's traveling through. This is like the Michelson-Morley experiment. And so now, because of this constant speed of light, we need to reformulate these Galilean transformations to take into account how, what is the actual symmetry group of transformations that physics is invariant under. And so although these were discovered before, the so-called Lorentz transformations, they were discovered before special relativity as elements of the Poincaré group, it was Einstein that really said, okay, now we have this similar situation where we have these two frames moving relative to each other. But instead of these previous Galilean transformations, the proper set of transformations that physics is invariant under are not the Galilean transformations, they're these Lorentz transformations. But, so the difference now here, so we have this x minus vt, so notice this looks very similar to the Galilean transformation before we had t prime equals t. So if v is much, much smaller than c, right? So if the speed of the relative motion between my inertial frames is small, then what happens in these? Well, this thing just looks like 1, right? I have 1 minus some very small number, so I can just neglect it, right? This is a very small number. So these reproduce the Galilean transformations in the limit where v is much less than c. But once we travel at relativistic speeds, right, close to the speed of light, then these terms start to matter. So that's the important thing, that these reduce to the Galilean transformation equations in the limit where v over c goes to 0. Okay, so that's fine. Now we just have some new way of translating x, but this is really the new and interesting piece right here. That we have this modification of clocks. Clocks run differently when we're traveling close to the speed of light, and in fact they slow down. So this concept of universal time that's kind of a big part of Galilean relativity and Newtonian mechanics is no longer true, right? Our clocks are running at different times. Yep?
So if I could go faster than the speed of light, would I have imaginary time?
No, you would not have imaginary time. So you note here that as v approaches c, so this is the point, c is the speed limit of the universe, right? This kind of tells us that right now, that we can't ever get faster than c. So this number down here is always positive. Right? But it's interesting that you say imaginary time. So imaginary time in statistical mechanics and quantum statistical mechanics is a concept that we deal with all the time. It's basically a classical system in d plus 1 dimensions can be equivalent to a quantum system in t dimensions, and that difference in dimension is an imaginary time. We can talk more about that at another time. So this is quite interesting and exciting. So now, once we can reach these high velocities, we no longer have the Galilean transformations, we have to deal with these Lorentz transformations. And so it's actually the Lorentz symmetry that is actually the larger symmetry, right? The Galilean transformation symmetry is some subset at low velocities. Yeah?
So is it saying that everything is, but before this was an idea, we were like the absolute reference frame, and now the absolute reference frame is sort of like the speed of light, and the closer you get to the speed of light reference frame. Yeah,
so the idea was that we never had to explore this, so we didn't even need to know about it, basically, because the implications of this symmetry group were never apparent to us. And so we could always say, okay, as you said, this is our absolute reference frame here on Earth, we don't have to worry about it, and we only have these Galilean transformations. So we're basically expanding our understanding of the possibilities of having different frames. Question?
Why does time affect you less if you're going close to the speed of light?
Does it affect you less? Yeah. Why does it slow down?
Why does it slow down?
Yeah, so this is basically a consequence of c being the speed limit of the universe. So you can't go faster than c, right? And so maybe this is something for, we can come back to this in detail later, but the point is if I'm on a spaceship traveling very close to the speed of light, and then I want to send you a signal, the fastest that signal can go is the speed of light. And so if you basically solve these equations, what comes out is that the person who knows they're traveling close to the speed of light, their local clock has to slow down. So it's not like in my frame, I don't know that my clock's moving slower, right? It's only when I bring you back together with me and we compare our clocks that time has moved more slowly for me than it has for you. So this is the so-called twin paradox, which is basically, you need to know that you're not in an inertial frame, which is the person on the spaceship that goes out, turns around and comes back, and then we compare our clocks, and I'm much younger than you are.
So our current justification of this phenomenon is our empirical equation.
No, well, the justification is just that the speed of light is the speed limit of the universe and it's a constant. So from that, everything else follows. Yeah. If you want to read an awesome book about the implications of special relativity, there's a great book called The Forever War. Has anyone read that before? Check it out. It's a really, really cool book. Basically, if we are fighting some war where we have to travel close to the speed of light, and you go out for a tour of duty, you come back and like 200 years has gone past on Earth and you've only been fighting for a year or so. It's very, very cool. Yeah?
I think I remember hearing this problem somewhere, but if you're on something that's traveling very close to the speed of light and then you fire a light beam backwards, how fast is the beam going?
Yeah, so it's still going in c, right? And so this is why we get this redshift that we talked about before. So there's a frequency shift of the light, but the speed is always the same. And that's exactly, we use that frequency shift, redshifting, to figure out that things are traveling faster the further they are away from us. And so the speed stays the same, but the frequency changes. And that's related, because that frequency changes, that's related to this clock slowing down thing, right? Frequency is like 1 over time. And there's we teach a lot of this stuff in various classes at UVM Physics 128. Check that out if you want to learn some more about special relativity. Okay, so next, well, I guess it's 2 weeks from now. So far we've done special relativity, right? My point was motivating why we need it. Well, now we have special relativity, which basically unifies Maxwell's equations with Lorentz invariance, basically. But now we need to figure out how can we merge special relativity. So special relativity is 1905. 1921, Einstein figures out a way to make special relativity consistent with Newtonian gravity. And so that's really that's the gist of it. That's what general relativity is. It's still a classical theory of space-time. This is what string theory is all about. How do we come up with a quantum theory? And I like this quote, which is I think due to Wheeler. Space-time tells matter how to move, matter tells space-time how to curve. So we'll come back to this at the next Feature Friday after the break. Cool, any questions? There's lots through it. All right.